Welcome back to the course on computer network and internet protocols. So, till now we have looked into the details of the transport layer and what different services is being provided by the transport layer. Now, we will take a specific example, a transport layer protocol which is widely used in the network. So, more than 80% of the traffic over the internet, it uses this transmission control protocol to transfer end-to-end data. So, we will look into the details of this transmission control protocol or TCP in short, and later on we will look into that how you can write an application with the help of socket programming to send or receive data over TCP connections. So, let us start our journey to learn the TCP protocol in details. Well, so this TCP, it was specifically designed to provide a reliable end-to-end byte streaming over an unreliable internetwork. So, what is mean by unreliable internetwork? By this time I hope it is clear to you that the network layer, the IP based network layer that we are considering, it is providing unreliable service because of this buffer filled up or buffer overflow from intermediate routers. There is always a possibility of packet drop, and whenever there is a packet drop from these intermediate routers, the network layer does not take care of that. So, the transport layer, if you want to provide a reliable service on top of the transport layer, that needs to take care of that packet drop. So, TCP is a protocol which supports this reliability on top of this unreliable internetwork. And by internetwork, we also look into that different parts of the network may have widely different topology. So, it may happen that one part of the network is using wireless technology, one part of the network is using WAT technology, another part of the network is using say optical communication technology. So, there can be this kind of various type of technologies which are there in the underlying network, and on top of that I need to transfer the data. So, for example, if you just think of an example when you are doing Facebook on top of your mobile. So, whenever you are doing Facebook on top of your mobile, so the first hop is wireless from your mobile to the mobile base station, that part is wireless. So, that uses a different set of protocol at the data link layer. Then from that base station to this mobile switching center, that part is the wired network, and that uses the high speed Ethernet network. So, there it uses another set of protocol. Now, from there from this mobile switching center to the service gateway, because say you are just accessing the Facebook server and the Facebook server is somewhere there in say USA. So, you need to send the data to USA. So, the gateway which is connecting this Asian network to the US network, that uses optical fiber cable in between. So, you need to transfer the data on top of that optical fiber cable. So, the underlying network is hugely different with different properties, and you can have different type of packet loss, delay, retransmission on top of this unreliable network. Now, TCP is a protocol which is designed to handle all these different challenges. So, let us look that how we use TCP to handle this different heterogeneity, this different challenges in the network. Well, so TCP dynamically adapts to the properties of the internetwork and is robust to face many kind of failures which may happen in the network, but this TCP protocol has a long history. So, the base TCP protocol it came as a part of this RFC 793. So, these RFCs are the full form of RFC is request for comments, and these RFCs are, you can think of it as a standard document for a protocol specification which is published by IETF, Internet Engineering Task Force, which is a global body to handle protocol standardization. So, the first version of TCP came in September 1981 as a part of this RFC 793, and then it has seen many such changes. So, I have just listed a few changes. This RFC 1122 which does some clarification on the TCP protocol, does some level of bug fixes. Then RFC 1323 which was designed an extension of TCP for high performance, then RFC 2018. So, the standard TCP protocol, it uses this go back in ARQ for flow control algorithm. So, RFC 2018, it uses this selective acknowledgement. So, we call it a version called TCP SAC, TCP Selective Acknowledgement Protocol, which uses this selective repeat protocol to handle the flow control mechanism. Then RFC 2581, it discusses about the TCP congestion control algorithm. RFC 3168, it uses one concept called explicit congestion notification. Even after that, there are multiple amendment over the basic TCP protocol. So, this TCP protocol has changed a lot from what it was designed initially in September 1981. So, a broad look on the TCP service model. So, all TCP connections, they are full duplex and point to point. So, point to point means they are between two end hosts, and full duplex means both host A and host B. Whenever you are making a TCP connection between them, host A can send data to host B, and at the same time host B will be able to send data to host A. So, TCP, it was designed for this point to point data transfer between two different machines. It was not designed to support multicasting or broadcasting, when you want to send data from one node to a group of nodes or from one node to a large set of nodes. So, for that TCP was not suitable. So, this TCP in a Unix based system, it uses the concept of socket which define an end to end connection. So, the concept of pipe that we are talking about during our discussion of generic service model of the transport layer, the same thing is termed as a socket in the context of TCP. So, a socket has 6 tuples, 6 parameters to uniquely identify a socket: the source IP, the source port, the source sequence number, source initial sequence number, the destination IP, destination port, and destination initial sequence number. The same thing that was designed to uniquely identify a pipe in a logical pipe in a transport layer. Now, once this host A and host B has set up a socket among them, then say host A want to send some data to host B, the reverse, host B want to send some data to host A. So, host B can use this write system call to write the data in this socket. So, host B will write the data in the socket, then this data will be delivered through this different layer of the protocol stack, received at the transport layer of host A. Then host A can execute the read call to read the data from that transport layer buffer, and this delivery, the reliable delivery, that will be taken care of by the transport layer, and the delivery of the packet to host A based on its IP address, that will be taken care of by the network layer, and that way with all these layers of the protocol stack. So, this logical pipe or logical socket, that defines the service model of a TCP protocol. So, all the services of this TCP protocol is implemented to support reliable data through this pipe, which is termed as the socket. So, in a Unix model, Unix based socket implementation, we normally run a single daemon process, which is called as a internet daemon or inetd. This inetd, it runs all the times at different well known ports. So, it is not like that all the time you have to keep one socket open. So, this inetd takes care of that. The inetd keeps on running on different well known ports and wait for the first incoming connection. So, when a first incoming connection comes, this inetd, it forks, that means it creates a child process with a new process ID and starts the corresponding daemon. So, for example, if you want to do a HTTP file transfer. So, HTTP file transfer, for that you have to run HTTP daemon which at the HTTP server, which runs at port 80. So, initially this inetd keeps on listening on port 80, and whenever you try to initiate a connection on port 80, then HTTPD pops up, because HTTPD is the daemon process which will use hypertext transfer protocol at port 80, that we have looked into the discussion of application layer protocol. So, it will start that daemon process and create the socket at port 80 at the client, port 80 at the server, and some random port at the client, and start receiving the HTTP packet. Similarly, for FTP type of protocol, the FTPD will start at port 21. So, few details about TCP. So, first of all, TCP connection is a byte stream, not a message stream. So, every byte is identified by a unique sequence number that we discussed during the generic service discussion of a transport layer protocol, and this message boundaries, they are not preserved end to end. That means, all the messages, or in TCP terms we call it as a segment that we have looked into, the segments may not be of the same size, so different segments may vary. So, here from host B to host A, it may happen that the first segment is starting from sequence number 100 and has a length 100. So, it goes from 100 to 200. The second sequence it goes from, this should be 200 to 1, it goes from 201 to 250. The third segment it goes from 251 to 400. So, that way this segment contains some 100 bytes of data, this segment contains, so this is say from 100 to 1 to 200, this contains 100 bytes of data, this contains 50 bytes of data and this contains 200 bytes of data. So, different segments may have different size and the size of the segment will be determined by the flow control algorithm that we will see later on. Now, in a hypothetical example, if it happens that well this segment 1 is received correctly by host A and say segment 2 and segment 3 are dropped, are lost. So, host B will try to retransmit bytes 201 to bytes 400. So, this should be 201. So, it will try to retransmit from bytes 201 to bytes 400. So, in TCP philosophy, it is not trying to retransmit two segments, rather it will understand that byte 201 to byte 400 has lost and it need to retransmit bytes 201 to bytes 400, not the two segments. So, the segments may not preserve, because in TCP everything is in the form of a byte stream and everything is identified by how many bytes I have sent or how many bytes I have received or how many bytes are in transition in the network. So, whenever it is doing the retransmission, maybe because of that rate control algorithm which we will discuss in details, it may happen that this entire thing is divided into two different bytes, two different segments. So, the first segment contains bytes 201 to 300 and the second segment contains bytes 301 to 400. So, now you can see that the earlier division that we had from bytes to segment, that was not being preserved here. So, earlier I have a small segment of 50 bytes and another large segment of 150 bytes. But now, whenever I am doing the retransmission, I found out, or better to say that TCP at host P finds out that well now I do not need to send a small segment of 50 byte, rather I can retransmit this entire byte with two segments of 100 bytes each. So, that is why we use this term that the message boundaries are not preserved end to end in the context of a TCP protocol. So, everything is byte streaming. One example, that the sending process, it does 4 512 byte writes to a TCP stream using the write call to the TCP socket. So, the application is sending 4 512 bytes of blocks to the transport layer, and if you remember that the transport layer architecture, you have this application, whenever the application is making a write call, that data is going to a buffer. So, the data is going to a buffer and the transport layer entity, it is reading the data from this buffer and creating the segments. Now, when it is creating the segments, if this sending process writes 4 512 bytes block to this buffer, now this data may be delivered as 4 512 bytes chunks, that means 4 512 byte segment, 2024 byte segments, or 1 to 2400 byte segments, or in some other way. It is not necessary that all the segments need to be of same size. So, there is no way for the receiver, when the receiver will receive that data, to detect the units in which the data were written by the sending process. So, here the sending process has written data in 512 byte chunks, but whenever the receiver process will receive the data, that is just the opposite thing. You get the data, put it in a buffer, receiver buffer, then the receiver application will make a read call to read the data from the buffer. and when the receiver application will make the read call to read the data from the buffer, it will again read certain number of bytes, and during that time it may happen that the this application is making a read call at 1024 bytes chunks. So, the sender has written it at 512 bytes chunks and the receiver is receiving it at 1024 bytes chunks. So, that may widely differ, and even the receiver does not know that at which or what was the chunk size when the sender has written that to the transmit process, to the transmission control protocol, to the TCP process. Okay. So, this is the header structure of the TCP protocol. So, the well known fields are already there that we have looked into, the source port and the destination port to uniquely identify the application through which you are making a communication. You have this sequence number to uniquely identify each packet. You have an acknowledgement number to acknowledging the bytes that you have received. I made a mistake while taking, I have told that sequence number for packet rather than that sequence number for the byte, because we are using byte sequence number. So, we should use the correct term here. Then the header length, the length of the header, certain flags. So, these are the flag bits. So, we will look into the flag bits in detail. Just for the few flag bits like this fin bit is used to close a connection, to finish a connection. So, if this fin bit is set, that means it is a connection closure message. If this SYN bit is set, SYN bit is for connection initialization. So, if this SYN bit is set, that means it is a SYN message for connection initiation. If this ACK bit is set, that means it is an acknowledgement message which is sending this acknowledgement number about the up to which bytes have been acknowledged by the receiver. Then you have this window size. This window size is the receiver advertised window size for sliding window protocol for dynamic buffer management. So, with this window size, the receiver is announcing that what is the available buffer space in the receiver side. This is 16-bit window size. So, we have 32-bit sequence number, 32-bit acknowledgement number, 16-bit window size. Certain checksum to check that the correctness of the received data. Urgent pointer, we will discuss about this urgent pointer later on. In brief, like if you want to send some message urgently by bypassing the queue, because if you look into the transmit queue, transport layer queue, that transport layer queue is a FIFO queue, first in first out queue. So, whatever byte has been came first, it will send that byte first. So, if you set the urgent pointer says that well, if you are sending some data from the application by setting the urgent pointer, that means whatever data you are sending from the application layer by setting the urgent pointer, you can do that with the help of socket programming. We will look into that. If you do that, then it will first create that segment and send it out with urgent bit set to 1. It indicates that this particular data is urgent, that should not wait inside the queue for this first come first serve or first in first out behavior. Then you have some optional fields and finally, the data which is coming from the upper layer, that means the payload for this packet. Well, we have looked into that, the TCP sequence number and the acknowledgement number. It uses 32-bit sequence number and 32-bit acknowledgement number. So, every byte on a TCP connection has its own 32-bit sequence number. So, because it is a byte stream oriented protocol that we have seen. So, TCP it uses sliding window based flow control. So, the acknowledgement number it contains the next expected byte in order, which acknowledges the cumulative bytes that have been received by the receiver. So, the example is like that. If you receive an acknowledgement number 31245, that means that the receiver has correctly received all the bytes up to 31244 and it is expecting the byte 31245. So, that way it is the cumulative acknowledgement number. So, once you are getting an acknowledgement number, it means that all the bytes before that number, immediately before that number, that has been received correctly by the receiver and it is expecting that particular byte. So, it is expecting byte 31245 and it has received everything correctly up to byte 31244. So, we looked into this earlier that in TCP this message boundary we call it as a segment. So, the sending and the receiving TCP entities they exchange the data in the form of segment. In general, a segment consists of a fixed 20 byte header plus an optional part. So, the header format that we have looked earlier, that TCP is segment header, followed by 0 or more data bits. So, if it is a connection message or connection closure message like the SYN message or the FIN message, you do not have any data, but if it is a data message, you may have additional data which is along with that segment. Now, let us see how these TCP segments are being formed, and as you have seen earlier that it is not necessary that all the segments will be of equal size. Here it will be little clear to you that why all the segments are not of equal size in TCP. So, TCP it can accumulate data from several write calls into one segment or split data from one write call into multiple segments. So, this write call with this write system call, you are sending a chunk of data from the application to the transport layer. Now, whenever the TCP is running, TCP say even if you have sent some just think of you have sent 1024 byte data, you are sending 1024 byte data as a single chunk from application layer to the transport layer with the help of this write system call. It may happen that the TCP may break that 1024 chunk into two 512 byte chunk and send two segments based on the need. The need I will discuss a couple of minutes later, or it can combine 1024 byte chunk together and create a single segment of 2048 byte and send it in one go. Now, how these segments are being created? That the segment size it is restricted by two parameters. The first parameter is the IP payload, the amount of data that you can put inside the IP fragment whenever it is going to the network layer, that is restricted to 65,515 bytes. So, your segment size cannot be more than that. The second parameter is the maximum transmission unit of the link. So, what is maximum transmission unit? That means, whenever you are considering an multiple network link from say source to destination, these links have a maximum transmission unit. So, that comes from the concept of data link layer. How this maximum transmission unit from data link layer comes into practice, we will discuss that in details when we discuss about the data link layer. But for the time being, just take it as an example or take it as an given postulate that for different technology the maximum transmission unit is different. So, for example, if this link is a Wi-Fi link, you have one MTU. If this is an Ethernet link or a WAN link, you will have another MTU. If this is an optical fiber link, you will have another MTU, maximum transmission unit. So, the maximum transmission unit is basically that at a single go, what is the amount of data or what is should be the amount of data that you can put inside the packet. So, what TCP does? TCP uses this write calls from the application to write the data in the TCP sender buffer. So, here in this example that the application makes a write call to write data in the transport buffer, and the sender it maintains a dynamic window based on the flow control and the congestion control algorithm. So, ideally your sending rate was minimum of network rate and receiver advertised rate. So, whenever we convert this in the window form, your sender window size will be minimum of one window size which will be given by the congestion control protocol. So, earlier we are talking about that in case of congestion control, you increase the network rate from a low rate to very high rate using this additive increase principle. So, to increase that rate, it is just like you are increasing the window size. So, if you are increasing the window size, that means at the same instance of time you will be able to send more data. So, you will be able to increase the rate. So, this congestion window gives a indication that well, if your window size is 1, so you can send 1 byte of data. If your window size is 2, you can send 2 bytes of data simultaneously. If your window size is 4, you can send 4 bytes of data simultaneously. So, you have this congestion window and the receiver advertised window size, minimum of that. So, you have this sender window size. So, this sender window is dynamically triggered, dynamically updated based on the receiver advertised window size and the congestion window size that you are gradually increasing in the additive increase phase, and whenever a congestion is detected, you are dropping it again to a small value or a minimum value. So, this flow and congestion control algorithm, it will use this window size, and based on that your segment will be created. So, this is the algorithm for creating a segment. So, today's implementation of TCP, it uses this path MTU discovery, a protocol which is there in the internet control message protocol part, as a part of the internet control message protocol, which is implemented at the network layer. So, what it does, it tries to estimate that what is the MTU of all the links in the path. So, by getting the information about all the MTUs of the path, of the link in the path. So, as an example, if it happens that, well, so these are the links. So, this is your source and this is your destination. So, this link support 512 byte, this supports 1 KB, this supports 1 KB, and this supports say 256 byte. So, if that is the case, that means ideally you should not send data more than 256 byte in this entire end-to-end path. So, that is the task which is done by this path MTU discovery mechanism inside the ICMP protocol, internet control messaging protocol, and it sets up its maximum segment size during the connection establishment. So, during the connection establishment, by exchanging this message at the network layer, by getting this feedback from the network layer, it sets up the maximum segment size. This maximum segment size sometimes depends on other parameters like the buffer implementation, what is the amount of data that your buffer can hold at one go. Now, the sender, it checks the window after receiving an ACK, because whenever you are receiving an ACK, with that you have this currently receiver advertised window size, which will tell you that how much of data the receiver can hold. So, if the window size is less than MSS, that means the receiver can, whatever the receiver can hold, it is less than your maximum segment size. So, you construct a single segment. Otherwise, if that is the case, if your receiver window size is more than your MSS, say your receiver window size is 2048 byte, and that is your receiver window size, and your MSS is 1024 byte. That means, you can, if you have 2048 byte of data in your inside your sender buffer, then you can create two different segments with 1024 bytes. So, that way you create it 2024 byte segment and transfer it over the network. So, that way dynamically this segment size are get adapted based on this particular mechanism, by looking into that what is the receiver advertised window, what is your maximum sender size, as well as what is the amount of data which is there in the sender buffer. It may happen that the sender buffer have only 10 byte of data. If the sender buffer has 10 byte of data, then if you just keep on waiting for whenever you will get 1024 byte, because it is equal to your maximum segment size and you will transmit that, you may unnecessarily delay certain message. So, that is why we will look the mechanism in details later on, but broadly even if you have a small amount of data in the sender buffer, you do not wait for the data for the maximum segment size. Whatever data is there in the segment size, you transfer that data. So, that is why many of the times it may happen that if the application is not generating sufficient data, then you can push the data in the network which is less than where the segment size is less than your maximum segment size. So, the challenges which is there in the TCP design, and from here we will look into the design in details. First of all, the segments are constructed dynamically. So, a retransmission that do not guarantee that the retransmission of the same segment. So, that we have seen earlier, that earlier you had one segment of 50 bytes, another segment of 150 bytes, and whenever you are making a retransmission, you are making two retransmission of 100 bytes each. So, a retransmission may contain additional data or less data or a rearrangement of the segments. And sometimes these segments may be out of order, because TCP it does not determine the path, the network layer is determining the path. And the network layer, it may happen that for one segment, one packet which is coming from the application, the network layer packet, it decides one path, for another packet it decides another path because of this load balancing or many other mechanism in the routing protocol. and because of that these segments you may receive the segments out of order at TCP. So, this TCP receiver it should handle the out of order segment in a proper way, so that data wastage is minimized. So, if you are applying this go back in ARQ, and if you just think of that, well, if I am receiving something out of order, I will not put it in the buffer, because anyway the sender will retransmit the entire thing altogether. That is not a wise idea. Why? Because a small example, because it may happen that at the this is the receiver, this is the sender, at the receiver side say you have received this much of data and then you have received this much of data. Okay. So, you have received from say 100 to 120, then 121 to 150 you have not received, then from 151 to some 500 byte you have received. Now, at this stage whenever the sender gets a timeout, the sender will try to retransmit this byte along with all the other bytes which are there in the sender buffer. So, this is the sender buffer, will send that retransmit that data. Whenever it is retransmitting that data, assume that in the first segment it has retransmitted from 121 to 160 in a single segment. So, the moment you are getting this, the receiver will get this, receiver will just chop out this byte from 120 to 149 and put that data here in between. So, this entire data now from 120 to 500 that has been received. So, the receiver can send an acknowledgement, and that is a cumulative acknowledgement saying that it has received up to byte 500. And the moment sender gets this, sender may stop sending this retransmission of the additional bytes, and it can update its window parameter accordingly and start sending the data from 501 bytes to the remaining. So, that way you can do the optimization to have a better utilization of the network resources. Now, we have this window size field in the TCP segment header. So, this window size field is used for flow control algorithm in TCP. It uses a variable size sliding window protocol, the dynamic buffering that we have looked into earlier. So, this window size field it tells that how many bytes the receiver can receive based on the current free size, that is buffer phase. And as we have seen earlier, that a window size 0 means the receiver does not have a sufficient buffer space. So, the sender should stall transmitting further data until it gets a good amount of or sufficient amount of window size advertisement. Now, TCP acknowledgement. So, the final TCP acknowledgement, it is a combination of the acknowledgement number and the advertised window size. Based on that, the sender will tune its parameter. So, that is the basic things about the TCP protocol. So, in the next class, we will go to the details of this sliding window based flow control algorithm, which is adapted as a part of the TCP. Thank you all for attending this class.